Okay, so we're going to start the next part of 13.2, and that is all about integration. So integration of vector valued functions. And there's not a lot of geometric kind of interpretation going on, but simply let me put it this way. So given r of t equals x of t, y of t, z of t, the integral of r of t dt is simply the integral of its components. I suppose you can, if you wanted to do this a little bit formally, I'm not going to do the full thing, but let me just kind of state this. So if you were supposed to define this a little bit more formally, so given, you would first actually probably define the definite integral. So given an interval AB, this is a time interval, if you wanted to compute the definite integral of r of t dt, how would you define it? You would define it exactly in the same way that you did the original ones. So you would split up the interval a to b into, say, n equal subintervals. So you'd have t0, t1, t2, so on and so forth, up to t sub n. And you would say, okay, well, suppose we were going to take right-hand sums just as a choice. You could have the sum of r of t sub I times delta t, where again delta t would be b minus a over n, and you would be summing from I equals 1 to n. And what would this do? Well, or what would we do with this? Sorry. We would take the limit as n goes to infinity to make finer and finer subintervals, and that would converge to our integral r of t dt, which is from a to b. But if you deconstruct this, essentially this is just happening in each component. This is the limit as n goes to infinity, summation of x of ti dt. Similarly for the y component, not dt, sorry, delta t here. Apologies. Delta t. This also should be delta t. I equals 1 to n. And similarly for the z component. And hence, what ends up happening is it just converges to the integral in each component. This is the integral by what we learned in first one variable calculus. This converges to the integral component-wise. So that's how you get to everything descending to the components, even if you start off with the formal Riemann sum definition. Okay, so what I'm going to do from henceforth is just assume that the integral of a vector valued function is, and it's true, that it's the integral of each component. So let's do just a couple of examples here. We'll do one indefinite example, and then maybe a definite integral example. So let's take r of t to be t sine of t squared e to the t, and let's take ln of t here. And let's find a general antiderivative. So we want to compute the antiderivative. A general indefinite integral gives you an antiderivative. We've seen that in single variable calculus. So we have the integral of t sine of t squared dt. the integral of e to the t dt, and the integral of ln of t dt. So what do we get? Well, here, the first part here, I'll just write the method. This is a u substitution. Here, this is a direct computation because the antiderivative of e to the t is e to the t. And here, we'll have integration by parts. So wanted to show at least something where show a couple of different methods. So let's compute each integral separately, and then we'll put everything together. For this, we'll set u to be t squared. Du is 2t dt, so that this becomes 1/2 the antiderivative of sine of u du, and that equals negative 1/2 cosine of u plus a constant. We'll call it constant 1. So this is equal to negative 1/2 the cosine of t squared plus c1. Okay, so that's our first integral. The second integral is just straight e to the t, so it's e to the t plus a constant. Call it c2. The last one is the integral of ln of t dt, which we do by parts. So u here is ln of t, dv is dt, du is 1 over t dt, and v is equal to t, and this equals uv, so t ln of t minus v du, oops, not equals, but a minus the integral of the t and the 1 over t cancel, and we get t ln of t minus t plus a constant. So overall, this guy, and this is constant 3, the antiderivative of ln of r of t is equal to negative 1/2 cosine of t squared, comma e to the t, comma t ln of t minus t, and then I'll put plus a vector constant, c1, c2, c3. So where c vector is c1, c2, c3. Okay, so that's an example of an antiderivative, a general antiderivative. We'll do one more example. So we want to compute, so the integral from 0 to 1 of r of t dt, where r of t is 1 over 1 plus t squared, and then we have a secant, squared here, and then we have a 1 over 1 plus t. Okay, so what do we get? Well, we need to compute each component separately. And we have the integral 0 to 1 of 1 over 1 plus t dt. Here we get the inverse tangent, or the arc tangent, whichever one you want to think about it, arc tangent of t from 0 to 1, which is arctan of 1 is pi over 4, arctan of 0 is 0, so we get pi over 4. For this one, we get the integral of tangent of t from 0 to 1, which is just a tangent of 1, because tangent of 0 is 0. And here we get the ln of 1 plus t from 0 to 1. This is the ln of 2 minus the ln of 1, which is the ln of 2. And so the integral from 0 to 1 of r of t dt, this is pi over 4, tangent of 1, and the ln of 2. Okay, so there's lots of exercises in the book as well as on WebAssign. But essentially there's nothing very substantially new here. It's just you're doing 3 integrals or a couple of integrals for each problem. So we'll stop here. This is the end of 13.2.